We're about to work through some practice problems. Now, for the best effect, you should always try these problems by yourself first. If you're watching this video for the first time, you can use that pause button when you see a problem and try it yourself. Unpause to see if we agree. An alternative is you can follow the links below and you can find a copy of these problems which you can work out at your leisure. All right, let's get going. Which of the following is the recursion for Newton's method for the function f of x equals 3x squared minus 1? All right, great way to start the test, a Newton's method problem. So Newton's method is about finding roots to polynomials, more accurately finding good approximations to roots to polynomials. Now, how does it work? And let's just remind ourselves, because when in doubt, we can always say, look, we can rederive it, right? So here is a function. We have our function f of x, and now our goal is to find the root. All right, now how does that work? Well, that turns out to be really hard, but what we can do is we can get estimates. We say, well, we're trying to find an approximation, so here is our current guess. We'll label it our current guess as our nth guess. And what we're going to do is we're going to say, well, let's get a better guess. So we come up and say, well, this is where we currently are, but locally it's flat. So what we can do is we can take advantage of that flat thing and follow it down and say, where do we hit? And that's our next guess. So we're following the tangent line down. Well, our tangent line, we can write down our formula. That's y is equal to the value of the function at our current guess plus the derivative at our current guess times x minus xn. Now, here's what's going to happen. When we solve for where we hit the axis, well, that means that we're going to set y to 0, and this x value is going to be xn plus 1. And now, rearrange it and solve for xn plus 1. So you subtract, divide, add, and what you get is the recursion formula, xn plus 1. So your next guess is your current guess with a correction, and it looks like minus f of xn divided by f prime of xn. All right, there we go. There we go. Good, good. Now, that's the formula. And if you remember that, basically any problem you see with Newton's method, you're going to get. For us, we want to explicitly say, hey, here's the recursion we want. So we just need to figure out what the recursion is. And we say, all right, well, we have our function. We also can say what our derivative is. The derivative of 3x squared is 6x. Derivative minus 1 is 0. So for us, our recursion looks like xn plus 1 is xn minus. And now we're going to plug xn. Everywhere we see an x, put an xn. So that's going to be 3xn squared minus 1. All right, divide by 6xn. Well, common denominator. So we can put it all together because you'll notice that none of these look like that. So you might have to do some algebra, but that's okay. Who doesn't like some algebra? And then so this is all over 6xn. So 6xn squared minus 3xn squared minus. Notice the parentheses here. Parentheses are point savers, right? We love our parentheses because they help remind us that, hey, you know what? This minus distributes in. So this is a plus 1. And now, what do we see? We have 3xn squared plus 1 over 6xn. There's our answer. And B. All right, so the answer was B. Good, good, nice. All right, well, lovely. I mean, Newton's method is pretty much remember the formula, and if you know the recursion, it's 3 points, right? And so just remember the recursion formula. And if you can't remember it, rederive it. It doesn't take that long. We have plenty of time. Plenty of time. given the information about f of x in the table below, use a Riemann sum to approximate this integral from 1 to 4 x f of 8 minus 2x dx using 3 equally sized intervals and midpoints. All right, so Riemann sums, the idea is we're chopping things up into rectangles. And so it's just a matter of saying, oh, we're going to add the areas of a bunch of rectangles. In this case, 3 rectangles. Okay, so to help us get started, let's think first about how we're cutting our interval up. Well, we know we're going from 1 to 4, because those are our bounds. So we'll draw ourselves a number line. We have 1 to 4. And then we know we're going in 3 equal pieces. So we're chopping this up into 3 parts, equally sized. Now, to figure out the steps, well, think about, okay, how far is it from 1 to 4? It's 3. If I divide 3 by 3, that means I'm taking steps of size 1. So it goes 1, 2, 3, 4. All right. Now, we need to pay attention to 2 things at this point. 1, what are our widths? Because we want to have our widths about us. So in other words, how big are these? Because that's part of the measurement of the rectangle. Well, these distances are all 1, so that's going to enter into our computation. The other thing is for each interval, we need to get a height. Now, the way we get a height is we're going to plug it into a function and read the value. So the question is, so which point? Because from 1 to 2, there are a lot of points you can pick. The 3 most popular are the left end, the middle, and the right end. And so the problem will direct us as to which one it wants. And in this case, it tells us it's after the middle. So we say, okay, what's halfway between 1 and 2? Well, 1 1/2, 1.5. I'll write it as 3 halves. Halfway between 2 and 3, 2 1/2 or 5 halves. Halfway between 3 and 4, 3 1/2 or 7 halves. All right, so those are the points which we're going to plug into the function. Now, speaking of the function, when we talk about the function, it's the part that we're integrating. So it's not really f of x, it's this whole part right here. This is going to be the function. So let's call this another name. We'll call it g of x. So this is where we get our heights. The dx is where we get our widths. So here we go. We have that our integral from 1 to 4 of this x f of 8 minus 2x dx is approximately, and this is going to be a really big approximation because 3 intervals is not that many, but that's all right. So we're going to take our width times our height. So for simplicity, I'm going to use g for just a second. So first rectangle, width 1, height, when we plug 3 halves in. Second rectangle is still width 1, height when we plug 5 halves in. Third rectangle, still width 1, height is when we plug 7 halves in. All right, so now plug them all in. So when we plug in our value for 3 halves, we're plugging it in to this expression. So, well, 1 times anything is just 1, so we're going to drop that. We have 3 halves times f of 8 minus 2 times 3 halves. Now, 8 minus 2 times 3 halves is the same as 8 minus 3, which is 5. Plus, plug in 5 halves. We have 5 halves. 8 minus 2 times 5 halves, well, that's 8 minus 5, so that would be f of 3. And then 7 halves, 8 minus 2 times 7 halves, that's 8 minus 7, so that's f of 1. Okay, all right. So, well, do we know these values? That's where the table comes into play. Okay, so this is approximately 3 halves. F of 5, well, that's 3. 5 halves, f of 3 is 1. And 7 halves, f of 1 is 4. All right, so let's see. We get 9 over 2 plus 5 over 2 plus 28 over 2. Okay, just carrying out that computation. 9 plus 5 is 14 plus 28 makes 42 over 2. And 42 divided by 2 is 21. And, that's one of our options. So there we go, 21. Now, be careful, right? If we had chosen, say, the left or the right, we wouldn't have gone 21. We would have gone something else. And I'm willing to bet it's one of these answers. So make sure you're doing exactly as described, because they will give you tempting alternatives. All right, well, there we go. We summed it all up. And just remember, Riemann sums, you're adding up a bunch of rectangles. So think of the widths, think of your heights, add them all together. Life is good. Find the average value for the function 2x squared minus 1 between 0 and 3. Okay, so this really tests us on a couple things. First off, what is the average value? And then can we carry out that computation, whatever it ends up being? So let's start by talking about what is the average value. And you can think of it sort of geometrically. The picture is you have some function. So here's some function, and we're going from some point A to some point B. And, well, it's not flat. Well, the average value would be, imagine that you had the same length from A to B, but now it were a flat rectangle. So, in other words, what rectangle has as much area as the curve does? And so the height is the average value. So how do you find that? Well, what you do is you say find the total area. So that's A to B of f of x dx. And then you say, well, that needs to match the area of this rectangle. And you know the bottom is length b minus a. So divide by b minus a, and that gives you the height that you're after. Okay, so that's the formula for average value. All right, well, now we plug it in for our specific case. So we know A and B. Those are our start and end points. So A and B. So we're going to have 1 over 3 minus 0. So all right, that is 1 over 3 integral 0 to 3 of the function 2x squared minus 1. All right. And, well, the last thing for us to do is to actually carry out this computation. So let's do it. So that's 1 over 3. And we can integrate. Integral of 2x squared. Well, we're going to add 1 to the power, so that's x cubed. We're going to divide by 3, so that makes 2/3 x cubed. And then we're going to subtract. Integral of 1 is x. Evaluate from 0 to 3. Well, when you plug in 3, what do you get? You're going to get 2/3 times 3 cubed, subtract 3. And now, when you plug in 0, you're going to get 0. Oftentimes, we don't even bother to write this down because we know it's going to be 0. It's really hard to recover from 0. All right, well, we're almost there. Notice we can knock out 1 3 here. So what do we have? We have 1/3, and then we have 2 times 3 squared. Well, that's 18, and minus 3. 18 minus 3, also known as 15. And 1/3 times 15 is 5. All right, so the average value is 5. All right, good. And there's the answer. Now, you might say, is there any sort of thing I can check for reasonableness? Well, one thing you can look at is think about, well, what can you say about the values for the function? And if you look at this, you say, oh, it's a parabola, and it's going to be going up. Starting at 0, it's at -1, and at 3, it'd be 17. 2 times 9 minus 1. So you'd expect it should be something roughly between -1 and 17. Well, it turns out 5 is roughly between -1 and 17. If we got an answer like 100, that would be pretty unreasonable. We'd want to go back and check our work. Maybe we forgot something like, the 1/3. And so pay attention and make sure you have the pieces in there. All right, well, that's not so bad. Great, let's keep going. If f of x is the integral from 4 minus 3x to 2x squared of 6t minus 2 over 2 plus t cubed dt, then f prime of 1 is... Okay, well, we've got to find that out. Now, the first reaction we might say is, are we really going to integrate that? And the answer is no. We're not even going to try. That is not completely hopeless, but basically hopeless. Okay, you can, in a pinch, get the antiderivative in this case, but it's, forget it, hopeless, hopeless, hopeless. So wait, how are we going to find the answer? Well, notice what we're doing. We're going to integrate and then take a derivative. And we say, well, wait a second. There's something about integrals and derivatives that they're somehow tied together in calculus. It seems very fundamental to the subject. All right, so there's a fundamental theorem of calculus. So this is really testing us on our fundamental theorem of calculus knowledge. So let's remind ourselves what that says. So it says the following. Suppose you're taking the derivative with respect to x of the integral from a to x of f of t dt. So this is the very simplistic version, and it's a good place to start. And the answer is that's f of x. So the way we think of it is as when we take this integral, we're really finding an antiderivative. The derivative of the antiderivative is what you started with. Okay, well that seems all good and reasonable. Now we say, okay, so one way we think about it is, well, really, this part here is going to go into the function x. All right, so it becomes f of x. Now, we can take this up a notch by combining this with the chain rule. And so we have a more general statement that says, suppose you take the derivative of the integral from some function h of x to some function g of x of f of t dt. All right, now what do? Well, you're going to sort of mimic what we did here, right? We plug whatever the upper part is into the function. So here, it's g of x. We're going to plug it in. So this is your f of g of x. So right, it's the derivative of the outside, but you plug the inside in times, by chain rule, the derivative of the inside, so times g prime of x. Now that's half of it. And just like when you do evaluations, evaluate from lower bound to upper bound, plug in the top, subtract, plug in the bottom. Bottom, same thing. Take the h of x, plug it in, f of h of x, times by the derivative, which is h prime of x. All right, so there we go. There's the fundamental theorem of calculus, and its nice generalization when you combine it with the chain rule. Okay, so that's what we're going to use here. So let's start by finding f prime of x. All right, so what is f prime of x? Well, we're going to follow the rule, and we have two pieces. So let's start by working with the top part first. So we have this 2x squared, and now everywhere where we currently see a t, we're going to replace that with our 2x squared. So this is going to become 6 times 2x squared minus 2 divided by 2 plus 2x squared cubed. Okay, that's the f of g of x. Now we need the g prime of x, the derivative of 2x squared, 4x. Good, good. And now the next step is we're going to say, okay, great. Now do the same thing with the bottom. The 4 minus 3x is going to be plugged in. Everywhere we see a t, put 4 minus 3x. And don't forget subtraction. So subtract 6 times 4 minus 3x minus 2 over 2 plus 4 minus 3x cubed. Okay, that's our f of h of x times our derivative of 4 minus 3x, which is negative 3. All right. Now you might be like, oh, are we really going to have to simplify that? No, we're not. We don't have to simplify it, right? Because what are we doing? We're going to do two things. We're going to simplify to get the number and plug in. Now the question is, do you simplify and plug in, or do you plug in and simplify? If you're going to plug in early, because it's so much simpler to work with numbers than to work with algebraic expressions. All right, well, with that in mind, let's go ahead. We're plugging in 1. So everywhere we see x, we put in 1. All right, f prime of 1. So 2 times 1 squared will become 2. So we get 6 times 2, which is 12, minus 2. Downstairs, we get 2 plus 2 cubed. That's 2 plus 8. And then we're plugging in 1. So 4 times 1 is 4, minus, 4 minus 3 is 1. So this is going to become 6 minus 2 over 2 plus 1. That's 1 cubed, times negative 3. All right. Well, let's clean this up. We see 12 minus 2 is 10. 2 plus 8 is 10. So this is 1. And 1 times 4 is 4. Here we have a minus and a minus, so those become pluses. 3 and 2 plus 1 will simplify. So we're left with 6 minus 2, also known as 4. And 4 plus 4 is 8. All right, so the answer is 8. And oh, yes, it is an option. Woohoo! Nice. And so there we go. And so now, once we had the tool, it became a lot simpler, right? Yes, that's why it's so useful to know things. Knowing things is half the battle. Of course, you also have to do the things as well. But all right, let's keep this going. Given that the integral from 3 to 11 of 4f of x plus 3g of x dx is 5, and the integral from 3 to 11 of 7f of x plus 5g of x dx is 8, then the integral from 3 to 11 of 8f of x plus g of x dx is one of these options. Okay, well, what? We don't know f. We don't know g. How are we supposed to find their integrals? Well, the sort of the punchline here is we don't actually need to find the integrals. What do we need? When I say we don't need to find the integrals, we don't need to find the functions, because that's hopeless. And what are we being tested on? Well, what do we see? Notice that everything has the same bounds. So we're all going from 3 to 11. So that's good news. And all the insides are the same. So what is going on here? Well, what we see is we have what we call linear combinations. So that means that we have things being added, and we also have things which have these scalar multiples, these 8s, the 5, the 7, the 4, the 3. So we can use properties of integrals to say, look, we can pull these expressions apart. All right, so let's rewrite what we have. So this first expression, we can say, well, look, this is really 5, and it's equal to 4 integral 3 to 11 of f of x dx plus 3 integral 3 to 11 of g of x dx. Now the second one, similar way, 8, that's equal to 7 integral 3 to 11 of f of x dx plus 5 integral 3 to 11 g of x dx. So this is what we're given. It's just another way of rewriting it using properties of integration. So we're being tested on our properties. And now, what do we want? We want to find the following. We want to find 8 integral 3 to 11 of f of x dx, and then plus integral 3 to 11 of g of x dx. So, what can we say? Well, notice we have these pieces here. We have these integral 3 to 11 of f of x dx's. And then we have these integrals from 3 to 11 of g of x dx's. All right? So if we think about these, whatever they are numbers. And so we can give these names. And so we'll just call them something temporarily, just for convenience. Well, let's call this part A. Let's call this part B. So we really have 4A plus 3B equals 5. And then we have here 7A plus 5B equals 8. And we're after 8A plus B. So we have two equations, two unknowns. Classic calculus math type problem. Two equations, two unknowns. All right. And this is, sometimes I like to call it the bread and butter, right? We just do these over and over and over again. It wouldn't feel like a calculus test if we didn't have at least one of these somewhere floating around. All right, so let's work through. We have 4A plus 3B equals 5. And we have 7A plus 5B equals 8. Now, how do we go about solving such things? Well, our goal is to cancel terms off. And because what do we have? We have two equations, two unknowns. We prefer one equation, one unknown, because that's really easy to solve. And so you get down to one equation, one unknown by somehow removing a variable. Now, you can do it in two ways. And one way is to get cancellation, or we sometimes call elimination. The other is substitution. Both are perfectly fine. Now, I prefer cancellation, if possible. So let's suppose we try to channel our cancellation. So we're putting on our, we're trying to eliminate a variable. And we pick a variable. And we say, all right, we want to eliminate either the A's or the B's. Well, let's suppose we want to eliminate the A's. Why not? Usually you look for one that looks easy to eliminate. Nothing jumps out as particularly quick. And say, okay, well, I want to combine these two equations in such a way that the A terms would go away. Now, currently I have a 4A and a 7A. 4 and 7 aren't great at mixing. But what we can do is we can say, well, let's scale it up. So we say, okay, well, what do 4 and 7 both go into? 28. So if we took the first equation, multiplied that by, say, 7, and the second equation, and we're to multiply that by 4, notice that the A's, you get 28A and 28A. Now they're like, ooh, they're really similar. So similar that if we were to subtract, it would go away. So that's our idea. So we're going to take 7 times the first equation, subtract 4 times the second equation. All right. Well, 28A subtract 28A gives us 0 A's left. 21B minus 20B, right? Because we multiply through. So 21B minus 20B gives us a single B. So 1 times B is equal to 7 times 5, which is, I'll write this down, 35 minus 4 times 8 minus 32. And the good news is we're now down to one equation, one unknown. Namely, we have B equals 3, and that's very easy to solve because there it is. We found B. Now, that's half of it. We also need A. All right. Well, no worries. Pick an equation. Doesn't matter. Let's say we pick the first one. Plug in what we know. 4A plus 3B would be 9 equals 5. 4A would equal 5 minus 9. That's negative 4. So A equals negative 1. So now we know B and A. And what were we after? 8A plus B. So we want 8 times negative 1 plus 3. Well, that's negative 8 plus 3, also known as negative 5. Aha! We found it! Woohoo! Yes! All right, so we have our answer. And this, what did we get tested on? We got tested on knowing our properties of integrals. that we can break them up. And this is actually really important properties of integration because it lets us take sort of like what looks like lots of complicated problems, one big complicated problem, and turn it into lots of smaller problems. Hopefully, none of them complicated. And so it's a good property to know. So it's a very good question for us to get tested on. And all right, good. Let's keep going. Find the integral of x e to the x squared dx. And we have options here. Now, there's sort of two approaches. So let's talk about our two approaches. One is pretend like this wasn't a multiple choice problem and then do it. The other is to say, hey, this is a multiple choice problem. Can we use that to our advantage? Now, sometimes the answer to the second question is no. Sometimes it's yes. Okay, so let's first off, let's do it in the forget it's multiple choice. All right, so we'll call that our non-multiple choice approach. So here we have our non-MC approach. All right. And so what do? We say, well, let's just work on this integral. We say, all right, x e to the x squared dx. Now, it's not one of our basic integrals. There's no algebra or trig available for us to manipulate here. That leaves us with the only hope we have of being substitution. Now, when we talk substitution, we often think substitution is an inside job. We're looking for function inside function. Well, there's a really good candidate for that here. Namely, the x squared, that's a function inside a function. X squared inside the exponential function. So we say, okay, well, function inside function, that says let's try it and see if it works. Well, if we plug it in, we get u equals x squared, and then du would be 2x dx. Oh, so close, but we don't have the 2. But here's the great thing. 2 is a constant. That's easy to move around. So we can move the 2 to the other side. So 1/2 du is x dx. Say, oh. So then this becomes the integral of e to the x squared would be e to the u. The x dx is 1/2 du. So this becomes 1/2 e to the u. Don't forget you tack on a constant. And also don't forget when you do a substitution and it's an indefinite integral, you have to go back to where you start. We can't leave our answer in terms of u. We have to go back to where we began. We started with x's. We have to end with x's. So 1/2 e to the x squared plus c. So, all right, is that an option? Well, no. There it is. B, 1/2 e to the x squared plus c. And we're done. Okay, now, that's if it's multiple choice. What's the multiple choice approach? Well, here, I'm going to just sort of say it out loud. And, of course, as I say, I'm going to say it out loud. I'll also write it down here. But what we want to do is say, look, we know one of these is the antiderivative. So what we can do is take the derivative of the answers, we should call them of the potential answers, a through e, and whichever one matches, that has to be the right one. Now, sometimes you can reverse engineer, sometimes you can't. So whichever gives x e to the x squared is the correct choice. So this is the, hey, I'm not great at taking antiderivatives, but I'm great at taking derivatives approach. So you say, all right, start with a. What's the root of e to the x squared? Oh, chain rule. You know, the root of e to something is e to something times the root of the inside. So the root of e to the x squared would be e to the x squared times 2x. Nope, doesn't match because it's not, there's the 2 missing. All right, how about the root of 1/2 e to the x squared? Well, it's 1/2 e to the x squared times 2x. The 2's cancel. You're left with x e to the x squared. It matches, we're done. Now, you may have had to go further and say, oh, well, x squared e to the x squared, that's going to be a product rule. That'll be 2 terms, 1/2 x squared e, again, you're going to get multiple terms with all the rest, progressive product rule. And so you're like, okay. So that's the idea. And all right, now, what should you do? And the answer is both are fine. You both get you full credit, because on multiple choice, we're not testing you on how you got to the answer. We're testing you on, did you get the right answer? So do what works for you. Get your points. Get as many points as you can. Just make sure you get the right answers as you do it. Don't do so many shortcuts that you get wrong answers. And yeah, one of the nice things about multiple choice is you only have to identify the right answer. You don't have to explain why the others are wrong. And so once you know, like, hey, this one has to be the right one, you can stop. You don't have to keep going. Isn't it wonderful? It's lovely. It's lovely. All right. Well, that's enough multiple choice problems, right? Maybe we should do something a little different. Find the following limit. If you use L'Hopital's rule, be sure to include justification that you can use it. Now, don't stress too much about that kind of a statement. What do you mean justification that we can use it? Well, we don't want you just wildly taking derivatives when you don't need to take derivatives. So the justification says we're really looking for something that looks like you approach 0 over 0, or you're going to infinity over infinity. We're looking for that kind of statement, because that's what you need to take L'Hopital's rule. Now, there's a couple of other things that you need. Things need to have derivatives, and you have to get a number out at the end. But to apply the process, this is what we're looking for. All right. So what do we have? We have one limit. Good. This will be quick. What's the limit as x goes to 0 of secant of x to the power 1 over x squared? Okay. Now, whenever you're taking a limit, the first thing you do is plug in. That's always the first thing. Okay, so we say, all right, what is this going to? This is going to, well, secant of 0 is 1, and 1 over 0 squared is big. So we write infinity. 1 to the infinity. And 1 to the infinity means more work. More work. That's right. We don't know. It's one of these indeterminate, or if you like, ambiguous expressions. Okay, now, some bad news. We cannot use L'Hopital's rule yet. Remember, you got to have that fraction thing going on. We don't have that yet. So we got to get that. And so in particular, we somehow have to bring this down. So what can bring exponents down? Logarithms. All right. So if you ever see something to a power, you're going to have a log involved. So let's for a second call whatever this limit is, we'll call it L. So we're going to take log of L. And the nice thing is, because log is continuous, we can push it past the limit. So that would be the limit as x goes to 0 of log of secant of x to the power 1 over x squared. And yes, I know there's lots of parentheses here, but I like to always hedge and make sure I have too many parentheses rather than too few. So I just want to make sure I understand how everything fits together. All right, now, properties of logs. Why do we do this? It's because the exponent, it's going down. Down, 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 it's going down. Woohoo! Right? That's the nice thing. So, this becomes the limit as x goes to 0 of log of secant of x. And this is a 1 over x squared, which makes it really easy to bring down because it becomes down right away as just an x squared. If it had been like an x, well, then we'd have to do a little bit of more, which we say, and then push it all the way down by flipping it upside down, and that's okay. But save ourselves a step. That's good for us. Okay, well, what's going on? Well, we test it. Say, okay, now plug in. right? You always plug in when you've done something to see how you're doing. Plug in 0. Secant of 0 is 1. Hasn't changed. Log of 1 is 0. 0 squared is 0, which equals more work. But not only does it equal more work, it equals the right kind of more work. We have our 0 over 0. We have our justification. We're ready to do le hôpital. Ah, le hôpital, mon ami. Okay, so we have our le hôpital. We put a little mark that we're doing something here. We could put a little comment here, apply le hôpital's rule, but something that says we know what we're doing. Now, the really good news, when we do le hôpital, it's not quotient rule, right? Oh, thank goodness. Quotient rule is so dangerous for us. It's easy to make mistakes, and it's complicated. It's take the dirt of the upstairs and take the dirt of the downstairs, and that's it. Okay, so we pick one. Let's take the dirt of the downstairs, right? We might as well do something that makes us happy. 2x, right? All right, now, okay, derivative of logs. How do we take derivatives of logs? Well, it's always fractions. So what we do is we say, okay, we have our fraction, and whatever's inside the log, that goes downstairs. So in this case, secant x. And what goes upstairs is the derivative. The derivative of secant is secant tangent. So we have secant x, tangent x. All right, well, we can clean that up a little bit. And so that's equal to the limit, because you can get the secants to cancel. Tangent of x over 2x. Okay, now, what does that go to? Plug in, right? Tangent of 0 is 0. And 2 times 0 is 0, which means we need more work. More work. Okay, but again, it's the hôpital. So we can do the hôpital. Now, I will say, in defense, you could from here, there are ways to do it without doing the hôpital. But why would we? We love it. We love to go, yes, it is the way of the le hôpital. All right, so again, we're going to mark that we're doing le hôpital. This becomes the limit as x goes to 0. And, well, okay, derivative of the denominator is 2. Now let's pause here. We now know game over, man. Game over, man. Game over. Because that's not going to go to 0. Whatever we get at this stage, that's it. All right, now what's the derivative of tangent? Derivative of tangent is secant squared. All right, now as you go to 0, secant squared goes to 1. So we get 1 over 2. We get a number. We're like, yes, 1/2. That must be our answer. Except that's not our answer. And like, wait, what? Steve, don't rain on our parade. Why are you doing this to us? Well, hold on. What did we find? Well, follow it back. So you have 1/2 is log of our answer. All right, so log of our answer is 1/2. We don't want the log, we want the actual thing itself. So we're going to take e, because e undoes logs. They're inverses of each other. And we get that our answer L is e to the power 1/2. Or, if you like, you can write that as square root of e. Exactly as you would have thought, right? Well, maybe not exactly like you would have thought, but it's not terribly surprising when you see something with something to a power. You kind of anticipate there's going to be an e involved in the answer, and that's all right. All right, there we go. What a lovely thing. So unexpected. What about this says square root of e? Nothing. And yet, that's the answer. Isn't math wonderful? Oh, that's great. All right, now on this one, it looks like we have 2 parts. And they're not really connected to each other, so it's just a practice for us of doing integration problems. And these are indefinite integrals, so there's no bounds. So all right, so let's look at them. Part A, we see we have algebra, and part B, we see we get trigonometry. Okay, good times ahead. Well, let's start with our algebra. Now, what do we want to do with algebra? Oftentimes our goal is to do things such as distribute, expand, break apart, and really we like to take big problems and pull them into small problems. So let's start by multiplying out the upstairs. We say, okay, well, this would be the same as the integral. X squared times 2x would be 2x cubed. X squared times 3 square root of x. And by the way, square root of x is just a fancy way of saying x to the 1/2. Oftentimes when you see a square root of x, you say, you know, if I want to make it more calculus friendly, make it x to the 1/2. Okay, so x squared, x to 1/2 becomes x to the 2 plus 1/2, which would be 5 halves. 4 times 2x, well, that would be 8x. And then 4 times 3x to the 1/2, well, that would be 12x to the 3 halves. All over x to the 3 halves and dx. Okay. All right. Good. Whoops. How did I get? That should just be a 1. Pay attention. 12x to 1/2. Okay. All right. Double check. 8x. X to the 5 halves. Good. And x cubed. Okay. Yes. Check your work. As the great philosophers often say, you should check yourself before you wreck yourself. All right. Now, I want to point out that this is actually good news for us, because what do we have? We have plus signs, and plus signs are secret code for saying, hey, that's pulling things apart. We like plus signs upstairs. Downstairs, not so much. Upstairs, oh yeah. All right. Now, what are we going to do? Well, we're going to put x to 3 halves under each term. All right, so what do we currently have? So we have this is the same as 2. Now, to take x cubed divided by x to 3 halves, you subtract. 3 minus 3 halves leaves us with a 3 halves upstairs. Plus 3, 5 halves minus 3 halves, well, that's 2 halves, or we can write that as just x. Here we have x to the 1 over x to 3 halves, and that would leave us with 8x to the minus 1/2. Here's x to 1/2, x to 3 halves. Now that's x to the minus 1, but minus 1 has sort of an unusual case. We have it where we like to leave it as 1 over x. And that's because x to a power has a fairly straightforward integral with one small exception, which is x to the power minus 1. In that case, we have to be a little bit careful because it's a slightly different expression. So how do we go? Well, we're now ready. We integrate term by term. That's the power of the plus. Okay, so we have the constant x to the 3 halves. We're going to add 1, so that'll get us back to 5 halves. All right, 3 halves plus 1 is 5 halves. I don't know why I said back to 5 halves. It'll get us to 5 halves. Then multiply by the reciprocal, 2/5. The next term, we have 3. Add 1 to the power, makes squared. Divide by the reciprocal, 1/2. Then we have x to the minus 1/2. So when we add 1, that becomes x to the power positive 1/2. Multiply by the reciprocal, which would be 2. And now the 1 over x, when you integrate that, that gets you log x. And of course, don't forget plus c. Every indefinite integral needs a plus c. If you miss it, you'll lose a point. We don't want to lose any points. Points are precious. We want to keep them all. All right, well, we have the answer. Let's just clean up a little bit. So this is 4/5 x to the 5 halves plus 3 halves x squared plus 16 x to 1/2 plus 12 log of x plus c. All right, no big surprises on that one. All right, the second one. Find the integral secant theta over secant theta minus tangent theta d theta. Okay, well, what do we do? Well, our goal here is to try to think of a way to integrate this. Now, we have an obstacle, which is this right there. Now, plus is upstairs. Oh, yeah. Plus is downstairs. They are a pain, and you have to think of a way to get rid of them. And so we say, okay, we want to do something to get rid of the plus or minus downstairs. And we start thinking, well, what are some things that we know about secants and tangents? We dig into our treasure trove of facts about secants and tangents, and we don't have very many, but we have one. That's very handy, and we have some backups, but let's start with what we can probably have the most important one, which is secant squared is equal to tangent squared plus 1. All right, this is the Pythagorean identity, so that's a nice little fact. Now, how can that help us? Well, one thing it tells us is if you move the tangent squared across, you get that secant squared minus tangent squared is equal to 1. And you're like, oh, that could be helpful because it's helpful. Now you might say, okay, so we just put a bunch of squares and we're good to go, right? No, unfortunately not. We can't quite do that. But what we can do is say, well, how do we turn secant minus tangent into secant squared minus tangent squared? We use the conjugate. That's right. It's been a while since we've said that out loud, hasn't it? Okay, so let's see. We're going to say that this is equal to the integral. And this is still nothing to do with calculus yet. This is all about saying, look, there's not a lot we can integrate, so what we have to do is think of ways to rewrite it. The majority of calculus when it comes to integration is how can you rewrite this expression until you get to something you can actually do. Because the number of things you can actually do is very small. And so it's all about manipulating what you have to get to something you can work with. So here we're going to multiply by secant theta plus tangent theta downstairs, and we'll do it upstairs. The reason we're doing it both top and bottom is because that lets us say, look, you're multiplying by 1. Multiplying by 1 is good. Adding 0 is good. And but multiplying by something not 1, multiplying, adding something not 0, no way. So you have to be really careful. You have to say, look, this really is the same. It's just written in a different way. All right, so if we carry this out, because of the conjugate, we get secant squared. Then we get secant tangent minus tangent secant, and that cancels. That's why we like the conjugate, minus tangent squared. So downstairs, secant squared minus tangent squared. Upstairs, distribute the secant through. Secant squared theta plus secant theta tangent theta. All right, so that's our current integral. But now we're like, wait, hold on. We did all this work to say this denominator is 1, and that's correct. And, well, since it's 1, we can just get rid of it, right? Yes! Woohoo! Nice! So this is the integral of secant squared theta plus secant theta tangent theta. Now, are these things that we can integrate? Are they on our list? I claim they are. Well, okay, so integral of secant squared. What's something whose derivative is secant squared? Tangent. Okay, so the integral of secant squared is tangent. What's something whose derivative is secant tangent? Secant. So the integral of secant tangent is secant. So you get tangent theta plus secant theta, and of course, don't forget your constant. And there we go. So we can do some algebra, and we can use trig identities. So trig identities can be fun and also challenging. The problem with trig identities is there's a lot of trig identities, but there's only a small handful which will come into play. And so you don't need to know that many. All right, good. Whew, well, you made it. More practice with integration, right? It's not surprising. This part of the class is all about integration. So it's good that we're getting our practice in. Find the area for the region bounded by the curves x equals y cubed minus y, and y equals 1/3 x, where y is greater than or equal to 0. And it's the shaded region in the figure below. And so we say, oh, yeah, we have a figure below. And we can identify some curves because we say, well, y equals 1/3 x, that's pretty easy to identify. That's the thing that looks like a line. So that must be the line part. X equals y cubed minus y, well, that has to be the other part. So here we go, x equals y cubed minus y. Now, how are we going to find area? Now, normally we think of areas like top minus bottom, but that's not the only way we can do it. So top minus bottom is if we're slicing it into vertical rectangles. But we can also slice it into horizontal rectangles. So generically, we can think of it as follows. So our generic area formula says area is integral from start to stop. And then we're going to have a width and a height. Now, what does this mean? So when we step back and say, what is integration about? Integration is about finding totals. And totals can mean different things in different contexts. And so area is just one example of a total. It's a total area. And so we say, okay, we're splitting it up into small pieces. And so here, when we talk about area, our small pieces are little rectangles. Here's one rectangle. And now add them up. So when you see an integral sign, think of it like, oh, I'm adding something up. I'm finding a total. Now, for us, we say, okay, we have our totals. We have our rectangles. We're going to do our horizontal rectangles because we want to integrate with respect to y. You might say, but why do you want to integrate with respect to y? Well, there's two reasons. One is if I try to do vertical slices, notice how I have one change of behavior. So below 0, I have this little tiny bump where I'm going from curve to curve. Above 0, I'm going from the line to the curve. So I'd have to split up into two integrals. Even worse, I'd have to figure out what is y as a function of x. That's pretty hopeless here. Now, do there exist formulas? Yes. Would they fill up the page? More than that. They probably fill up a couple of pages. Would we get really frustrated? Incredibly so. Can we do it by slicing horizontally? Oh yeah. So do it in the way that makes it easiest. And so some problems you slice vertically, some you slice horizontally. It's at the end of the day, it's all the same. You're finding area. So you say, okay, so we have these little tiny rectangles. Now, that says, what about our height? Well, our height, that's this little tiny height here. And that would correspond with our dy. Now, what about our width? So that's between the two curves. And so for width, you channel the same thing you do for height. So for height, it's top minus bottom. For width, it's left minus right. Why? Well, you should think of it as high value, low value. Right minus left. Did I get that? I may have said that backwards. Right minus left. Okay. High minus low. I apologize if I accidentally transpose those. Okay, so right minus left. Or you can think of it as high minus low. High minus low. Okay, so here we go. In our case, we're going to have, it's the integral of, and we're doing this with respect to y. So we say, okay, what's on the right-hand side is this line, y equals 1/3 x. Well, we need to write it in terms of x. So it's x equals 3y. So it's 3y subtract the left hand, y cubed minus y. All right, dy. Are we done? No. We need the bounds. Now, this number looks pretty clean, so that looks good. So I'm going to guess that that's a 0. But where is this at? Now, you could say, what's the x value? Or you could say, what's the y value? In our case, we really want the y value. How do we find it? Well, set the two equal to each other. When does y cubed minus y equal 3y? Now, you can solve it, or you can start making educated guesses. There's nothing wrong with educated guesses. In fact, a lot of math secretly has the educated guess as a tool that you draw from. And so don't underestimate the value of good guesses. And if you see a problem on the test, we're not going to give you exotic numbers. We're talking like 1s and 2s and 3s, right? So if nothing else, say, does 1 work? No. Does 2 work? Oh. Or does 3 work? Oh. It's like, that's the kind of thing you do. All right, so just keep that in mind, because sometimes we do things like that. All right, so, well, this is the same as y cubed minus 4y equals 0, or y times y squared minus 4 equals 0, or y times y minus 2, y plus 2 equals 0. So we get y equals 0. All right, whoops, sorry about that. Y equals 0, which is the one we already talked about. And we get y equals negative 2, which is off of this picture because we don't want negative 2. We want greater than or equal to 0. And then we get positive 2. All right, so it's that y equals positive 2. Now, we can figure out that x happens to be 6. Okay, so what number goes here? 2 or 6? 2. How do we know that? Well, because it's an integral with respect to y, everything's in terms of y, which includes bounds. So it's y equals 0 to y equals 2. So we want to talk about where does y go from, and it goes from 0 to 2. So make sure you put in the right bounds. All right, well, we can clean it up just a little bit, but we're almost done. Almost done. So what can we do? We can distribute the minus through. We can combine. You have 3y minus y makes 4y. So we say, all right, that's the same as the integral 0 to 2 of 4y minus y cubed. And all right, so that would become integral 4y is 2y squared. Right? Add 1, divide by 2. Integral of y cubed, 1/4 y to the 4th. And plug in from 0 to 2. And when you plug in 2, 2 times 2 squared, well, that's 2 times 4, that's 8. 2 to the 4th is 16, times 1/4, so that would be minus 4. And when you plug in 0, you get 0 and 0, okay, so it's 0. And so 8 minus 4 is 4. Good. And that seems like a reasonable-ish answer. All right. Now you might say, well, how can I be kind of more confident other than saying it's reasonable-ish? You can do things such as say, well, hey, is it positive? If you had gotten a negative number out for area, that's bad. Now, it's true that integrals can be negative, but that's just generically because some totals can be negative, but area is a measurement. It shouldn't be negative. So if you got a negative out, something went wrong, probably you somehow mix these up. So be careful. The other thing, of course, is maybe you did your integral wrong. The other thing you can say is, well, let's just think about the picture here. We actually see that this whole rectangle here is 2 by 6. So that would be a total area of 12. And so this here is half. And this even if you put this in, that's less than half of the area. So it should be less than 6, but not too much less than 6. It should be 4-ish sounds about right. So even sometimes eyeballing it says, yeah, that seems like we're in the right ballpark. And so, yeah, there we go. We found our area. Woohoo! Yay! Hurrah for us! Hurrah for us! Evaluate the integral from 0 to 2 of 3x minus 2 times the square root of 4 minus x squared dx. All right. Well, how are we going to do this one? Now, it's not so clear how to start. You might say, well, 4 minus x squared, there's a couple of things, right? You can try a substitution, and the derivative of 4 minus x squared basically looks like an x dx. Don't worry about the constants. And I say, well, I see an x on that part, but not on that part. But you also say, hey, square root of 4 minus x squared, it feels kind of circle-like. Maybe I can use that. Well, that's fine if you didn't have the 3x, you just had a constant. And I say, oh, that's not good. But now, here's sort of something we can say. Wait a second, I see this minus sign here. Now that's a good minus sign. You might say, well, wait, why not? Why isn't this one a good minus sign? Well, that one is not a good minus sign because it's on the inside. Just like minus signs in the denominator, minus signs inside functions are not good. But minus signs on the outsides can be useful. So one thing we can do is we can say, we can rewrite this. This is the same as the integral 0 to 2 of 3x square root 4 minus x squared minus 2 square root 4 minus x squared. So multiply through. And here's the great aha, is we can further say, look, these are two completely separate integrals. Now, why would we want to separate? Well, it turns out that sometimes you want to use different techniques on different parts. So by separating them, you say, look, I'm going to do two things. Something over on this side, something over on this side, and I want to, because they're separate, I can use separate ideas. And so there is a power that comes with separation. So we have 3 integral 0 to 2 x square root 4 minus x squared, and then minus 2 integral 0 to 2 square root 4 minus x squared dx. Okay, so we're going to work on these two pieces separately for a few minutes. Okay, well, let's work with this first one. All right, so here is number 1. All right. Now, looking at this integral, let's go back to what we said. Well, can we do a substitution? We can substitute on the inside. So suppose you let u equal 4 minus x squared, right? You always think about substituting on the inside. Now, we kind of did a mental computation and said, well, the problem is the minus 2. We don't have that anymore. So when we look at our du, that becomes minus 2x dx. Or we can say minus 1/2 du is x dx. So that this becomes our integral. The square root of 4 minus x squared becomes square root of u. And square root of u, by the way, let's make it our calculus-friendly way, write square roots as powers, so to the 1/2 power. The x dx becomes a minus 1/2 du. And because it's a definite integral, we want to update our bounds. And we always update our bounds as we go. Because we update our bounds, we never have to go back at the end, which is lovely. We really don't want to have to go back at the end. So we say, okay, so updating our bounds. Now, our old bounds are x bounds. So we're talking x equals 0 to x equals 2. All right, so just to emphasize, this is x equals to x equals. We want to go to u equals to u equals. Okay, so when x equals 0, 4 minus 0 squared is 4. When x equals 2, 4 minus 2 squared is 0. All right. Now you might say, I don't like the fact that I have 4 down and 0 up. Well, that's okay. You can swap. If you change the order, what does that do? Changing the order changes the sign. Well, we already have a minus, so we can say, this is the same as the integral from 0 to 4 minus minus makes it just 1/2. All right, and don't forget your du term. They are very persnickety. They always are like, did you get that du term or that dx term? Write them down. Write them down. They play an important role. All right, well, now we're ready. We're most of the way. So we say, okay, we integrate. So we have 1/2. Now, u to the 1/2, when we integrate, we're going to add 1, so that makes it 3/2, and then multiply by the reciprocal 2/3. Evaluate from 0 up to 4. So the 2's cancel, so that gets us 1/3, and 4 to the 3/2 is what? Well, that's 4, you can think of it as 4 cubed, which is 64, and then the square root of 64, which is 8. Or you can think of it as 4 to the 1/2, which is 2, and 2 cubed is 8. All right, so it's 8. All right, so 1/3 times 8, and when you plug in 0, you get 0. So you get 8/3. All right, so that's number 1. Let's talk about the second one. We'll call it number 2 because we're not very creative, right? We have integral 1, integral 2. Now, here, substitution wouldn't work because we don't have an x floating there. And I go, great, so what can we do? Well, we can think of it by geometry. So what we can do is say, hey, this is the integral of something. It can represent an area. What curve do we have? Well, if we think about our curve, y equals the square root of 4 minus x squared, say, well, that sounds kind of familiar. It sounds like it's something we've talked about before. Well, if you square it, that becomes y squared equals 4 minus x squared. Or that becomes x squared plus y squared equals 4. And like, oh, circle. That's a circle because it's a circle, right? Okay, great. It's a circle of radius 2, centered at the origin. Now, we don't want the whole circle. We only want from 0 to 2, and we want the positive part. So that says we want the quarter of a circle. So this is really an area, which is 1/4 of a circle. So we can say the integral from 0 to 2, square root of 4 minus x squared dx equals 1/4 the area of circle of radius 2. Now, the good news is we know how to find the area of a circle of radius 2. You take pi r squared, which is, well, 2 squared is 4, so we end up with pi. All right, so by separating out the integrals, we can apply different ideas to the two pieces. Now we can sew it back together. So we have 3 times 8/3 minus 2 times pi. Well, 3 times 8/3 is 8, and 2 times pi is 2 times pi. So our final answer is 8 minus 2 pi. Huzzah! We got it. What a lovely answer and a great way to finish our practice. All right, well, I hope you were able to do these problems, and the more practice you get, the more natural these problems will become. And oftentimes when you start integration, it seems like, man, this is really weird. Am I ever going to get it? You will. You can. But it takes time. It takes practice. You can do this. I believe in you. I know that you're putting in the work. And so keep putting in that work. Have it pay off and be wonderful. I really hope that you are going to do great on that test. All right. Thank you. Bye.